When we're talking about a limit, we're talking about the y value, the intended height of any type of function f of x. Remember, the function doesn't actually have to reach that height. It could have a hole there, or it could be going to on and off to infinity, and we'll talk about what happens when that occurs. And the way we write it is we have the limit as x approaches c of f of x. Please be careful to make sure you have all of those pieces. You have to have a limit of something, so you have to have that f of x written there, some sort of function. And the way that we read that is the limit of f of x as x is approaching some value of c. So c is actually going to be a number. It is an x coordinate. So what we're really looking at is if I give you an x coordinate, what is the y coordinate? That's just bottom line what we're talking about. When we talk about a limit existing, we're talking about the limit as x approaches c of f of x exists if and only if, that's what that IFFF means, of the limit as x approaches c from the left, and we denote a negative by approaching to the left of f of x, and that is going to be equal to the limit as x approaches c from the right, and the way that we denote to the right is with that little plus sign of f of x. And so the way that we read it is the limit of f of x exists if and only if the limit of f of x on the left equals the limit of f of x on the right. And now I'm going to give you several examples to show you what I mean by that. And we talk about a limit failing to exist in certain situations, such as if a function approaches a different number on the left-hand side than the right-hand side, such as if I had to have something like this. Oops. Wrong color. And I have a linear function coming up here, and I have a nice little hole there, and then I have my linear function coming down here. So as you can see, as I approach 0, I have two different y values, essentially. And so that, in this case, as x approaches 0, my limit would fail to exist. The function increases or decreases without bounds, so that's a fancy-dancy way of saying my function is going to positive or negative infinity, such as in this case. In this case, I have, they're both, as they approach 0, they're both going to positive infinity. That's what it means by increasing or decreasing without bound. Finally, we're talking about a function that oscillates between two different numbers. So we're talking about maybe some sort of sine wave that just kind of bounces back. So it gets closer and gets closer to 0 and then spans back out again. So it just kind of just bounces between two different values. So now let's look at an example. So we're going to use the graph below to find the limit, if it exists, for this function. And as you can probably see, I have a little hole that's located right here. And so in terms of limits, we're not really concerned about that hole. We're more concerned about, essentially, if you want to look at the lines that are approaching that hole, are they going to the same spot where the hole is? And so I have the function f of x is equal to 2x squared plus 7x plus 3, and that is all over x plus 3. And so what we're going to look at is, for the first one, is the limit of f of x as x approaches 0. And so we're looking at our function as we're approaching 0. So I want to look from the left-hand side, and I want to look from the right-hand side. And am I approaching the same y coordinate? So the x coordinate is 0. And so my y coordinate, I want to see, does it approach the same value, which is, in this case, 1. And so my limit of f of x as x approaches 0 is equal to 1, and that's all we have to write. So now let's look at the limit of f of x as x approaches negative 3. So we're going to go to, we have negative 3 located right here. That's our x coordinate. So let's look down to see, this It looks like they're focusing in our hole. And we want to see, does the limit from the right-hand side equal the same spot for the left-hand side? Or sorry, I said that backwards. From the left-hand side is equal to the right-hand side. And as you can see, it's approaching the same y value, which is equal to -5. And so we're just going to go ahead and write -5. All right, now we're going to look at C for number 2. We're going to find the limit if it exists. And we're talking about an absolute value. And if you notice in the numerator, there's an absolute value. And so when we talk about absolute value, I just want to help you just remember what we're talking about here is, let me go ahead and get my coordinates up here. And the parent function for the absolute value kind of looks like some sort of V. It kind of comes up and then has a negative slope and then has a positive slope. As you notice, we'll have a negative slope on this side, on the left-hand side, and a positive slope on the right-hand side. And so when we look at the absolute value, we want to look at, in this case, if I go to -2, my function on, we want to check to see what's happening on the left-hand side and the right-hand side of -2. And typically what's probably going to happen is I'm going to have a negative slope on the left-hand side of -2 and possibly a positive slope on the right-hand side. So let's go ahead and check. And so I'm going to split this up. And so I'm going to write the limit as x approaches -2 from the left-hand side. And notice how I have that little negative that's kind of floating up in the middle of space right here. So there's my left-hand side. And I'm just going to go ahead and write, instead of writing f of x, I'm actually going to write the function x plus absolute value of x plus 2 over x plus 2. Well, if I'm talking about to the left-hand side, typically, remember I told you that's going to be a negative slope, so I'm going to go ahead and write, I'm going to go ahead and erase my absolute values here. And instead fix my 2, go ahead and write my parentheses, and I said that's going to be a negative slope. Well, those of you who are cancel happy, you'll notice that these two will cancel. And so I have essentially a -1. Well, let's check to see, is that going to be the same as on the right-hand side? So we're going to go ahead and write our limit as x approaches -2 from the right. And again, remember when I talk about the right, this right here, that denotes the right-hand side. And I'm going to go ahead and write the positive version of x plus 2, which I just have it in parentheses. You don't really need to have that. And let's go ahead and cancel. And finally, we're left with +1. Well, as you notice, -1 doesn't equal +1. They're two different values. And so since this happens, we're actually going to say, since they're not equal, our answer to the problem is D and E does not exist. All right, for number 3, we're going to use the graph below to find the following limits. And this is the graph of h of x. And we have two x-coordinates, a and b, located right here. So what we're going to check is probably the limits aka the y values for each of those x-coordinates, a and b. And so let's look at a. So we have the limit of h of x as x approaches a. And so we're going to go ahead and focus in right here. There's my a, and I want to check, does the limit on the left-hand side equal the limit on the right-hand side? So as I follow along my curve, I notice that I'm approaching, looks like about the y value of 1. And so now I'm going to check pretty close this time, because we don't really need to check so far away. And so I'm going to go ahead and start with this little dot here, and whoops. And just kind of come in, and you can see that I'm actually approaching the same y coordinate, which is also 1. So in this case, the answer to part A, the limit of of h of x as x approaches a is equal to, and we can just go ahead and write the number 1. So now let's check to see what happens when we approach b. So let's erase all that. And so here is my x-coordinate for b, and so I want to check to see what's happening with my y-coordinates. Well, let's check on the left-hand side. So I'm going to get pretty close. So it looks like my y coordinate is approaching, I don't know, 0.8. And so I now have to go to the right hand side. I have to kind of jump up here. And I have this Lydian function. I'm coming down, and approaching a hole. But my hole is located, I don't know, 2.8. Well, 1.8 is about 0.8. Is not going to equal 2.8. And so for part B, we're actually going to go ahead and write DNA because my limits aren't essentially meeting up to each other. Notice that there's a major break there. When that break occurs at an x-coordinate, then the limit's not going to exist because the left-hand side is not equal to the right-hand side. Finally, number 4, use a table to find the limit of g of x as x approaches 3. And so what I want you to notice right here is the x-coordinate for 3. There's 3. And so we want to ask, what is its y-coordinate? Well, if you look at it in the table, it says error. So we don't really have a y-coordinate. So we want to see on the left-hand side of our table, does that equal the right-hand side of our table? And so we're going to start on the left-hand side. And as you can see, I have my x value of 2.999. Well, its y value is 8.99. Well, as we get, let's get a little bit closer to 3, and that will be 2.9999. And so that's gets even closer. Its y-coordinate is 9.9998. Well, it looks like to me that I'm approaching the value of 10. So on this, when I'm approaching from the left-hand side, it looks like I'm approaching the value of 10. Let's go ahead and check the right-hand side. And so I'm a little bit further away. I'm at 3.01. Well, its y-coordinate is 9.99. Well, that's encouraging to hear because at least we didn't go to 10. We were not on 11. We didn't skip over the number 10 and it kept on going. It looks like we are approaching the same value. As I get closer to 3.001, which is closer to 3 than 3.01, its y-coordinate is 9.9999. Well, that's pretty darn close to 10 as well. So as I approach from the right-hand side, it looks like I'm getting to 10 as well. And so the limit of g of x as x approaches 3 is equal to, in this case, 10.